Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. In episode 101 of the Network Prepcast, we're beginning our journey into the world of dynamic routing protocols. This episode focuses on one of the most fundamental routing methodologies, distance vector routing, and its most prominent implementation, the Routing Information Protocol, commonly known as RIP. Dynamic routing protocols, unlike static routes that must be configured manually, enable routers to learn, share, and adapt routing information with one another automatically. These protocols reduce the need for constant administrative updates and improve responsiveness to network changes, especially in dynamic or expanding environments. Dynamic routing is essential because networks aren't always fixed. Devices come online, links fail, and new subnets are added. Having a routing system that can adapt to these changes in near real time is vital for network stability and efficiency. Distance vector routing offers a basic but functional mechanism for route discovery and sharing. It uses neighbor-to-neighbor communication and hop count as the primary metric for path selection. While not the most scalable or sophisticated model, distance vector routing provides a necessary foundation for understanding how routers make decisions dynamically. RIP is the best-known example of this category and will be our core focus in this episode. The term distance vector reflects how the protocol determines route selection. Distance refers to the number of hops, or router devices, between the source and destination, while vector refers to the direction or next hop router a packet should be forwarded to. In a distance vector protocol, each router builds its routing table based solely on information received from its directly connected neighbors. It does not have a full view of the network topology. This hop-based decision-making method is what sets it apart from more advanced routing techniques like link state protocols, which rely on a complete map of the network. Distance vector protocols are generally simple to implement. They have minimal configuration requirements and typically send routing updates on a fixed timer. For example, RIP routers send their entire routing tables to neighboring routers every 30 seconds, regardless of whether anything has changed. This method ensures regular communication between routers and keeps routing tables somewhat current, but it also introduces unnecessary traffic into the network. On the plus side, the simplicity of the update mechanism means distance vector protocols require relatively little CPU processing power, making them ideal for older or resource-constrained routers. RIP, or Routing Information Protocol, is the classic example of a distance vector protocol. First standardized in the 1980s, RIP was one of the earliest dynamic routing protocols used in TCP/IP networks. It uses hop count as its sole metric, and any destination more than 15 hops away is considered unreachable. This 16-hop limit ensures loops are avoided, but also severely limits scalability. Because of this limitation, RIP is best suited for small networks or educational environments. Despite being largely replaced in modern enterprise environments, understanding RIP remains essential for the Network Plus exam. There are two main versions of RIP, version 1 and version 2. RIP version 1 uses classful routing, meaning it does not include subnet mask information in its routing updates. As a result, it assumes default class A, B, or C subnet boundaries and cannot support variable length subnet masks. RIP version 2, however, is classless and does include subnet mask data, allowing for more granular and flexible routing. In addition to classless routing, version 2 supports basic authentication, making it slightly more secure than its predecessor. Most networks that still use RIP use version 2 for these reasons. RIP routers operate by broadcasting their entire routing tables to all neighboring routers every 30 seconds. These updates are sent via user datagram protocol on port 520. The receiving router processes the update by incrementing each route's hop count by 1 and comparing it to its current entries. If the new route is shorter, or if the existing route has expired, it will update its table accordingly. Because these updates are full table broadcasts rather than incremental changes, RIP consumes more bandwidth over time than more modern protocols. especially in larger topologies. One of the major drawbacks of RIP and distance vector protocols in general is convergence time, the amount of time it takes for all routers in the network to agree on the best paths after a topology change. Because RIP relies on timed updates, changes in the network can take minutes to fully propagate. This can lead to temporary routing loops, black holes, or inconsistent path selection. In addition, the path can be coded by bad path selection. Triggered updates, which are sent immediately when a significant change occurs, help speed up convergence. But they don't eliminate the problem entirely. These delays highlight the limitations of distance vector routing in more complex environments. To counter some of these issues, RIP employs two important techniques: route poisoning and split horizon. Route poisoning involves marking a failed route with a hop count of 16, signaling that the destination is unreachable. This helps prevent routers from forwarding traffic to a path that is no longer valid. Split horizon prevents a router from advertising a route back out the same interface from which it learned it, helping avoid looping behavior. These techniques improve reliability, but don't completely eliminate convergence delays. For the exam, understanding these mechanisms is key to identifying how distance vector protocols mitigate routing loops. Setting up RIP involves enabling the protocol on a router and defining which networks it should advertise. This is typically done using network statements that match the IP address ranges of the router's interfaces. Once enabled, the router begins sending and receiving RIP updates. You can verify configuration using show commands, which reveal which routes have been learned, how many hops away each one is, and which interface they were learned from. These commands are essential for troubleshooting and validating RIP behavior in any scenario. While distance vector routing protocols like RIP are simple and easy to configure, they come with several significant limitations. These include slow convergence, a lack of full network awareness, and vulnerability to outdated or incorrect routing information. Because of these shortcomings, RIP is rarely used in large or production environments today. However, it remains an important learning tool and is still found in certain legacy systems. Its predictability and simplicity make it an ideal protocol for illustrating core routing principles, particularly those that apply across all dynamic routing models. RIP still has valid use cases in modern networks, but they are quite limited in scope. It is best suited for small, flat networks where hop count will never exceed 15 and where the topology is relatively stable. Examples include home labs, classroom simulations, and simple internal segments that are not exposed to high volumes of dynamic change. In these environments, RIP simplicity and ease of configuration are more of an advantage than a liability. Since RIP does not require extensive CPU or memory resources, it can be run on lightweight devices with minimal impact. Modern networks that require faster convergence and greater scalability typically rely on alternatives to RIP. Link state routing protocols like Open Shortest Path First or OSPF use a full map of the network and are capable of making faster, more intelligent routing decisions. Hybrid protocols like Enhanced Interior Gateway Routing Protocol combine aspects of distance vector and link state behavior for improved flexibility and performance. For internet-scale routing between autonomous systems, Border Gateway Protocol is used. These protocols overcome the limitations of RIP by supporting more advanced metrics, hierarchical network designs, and robust loop prevention. Understanding the summary characteristics of distance vector protocols helps differentiate them from other types. These protocols rely entirely on information received from neighbors. They do not build a complete view of the network, and their metrics are usually very simple, typically based only on hop count. Distance vector protocols send full routing tables at regular intervals regardless of whether there are any changes. This can lead to increased bandwidth usage and unnecessary processing, especially in environments with frequent updates or large numbers of routers. Their reactive nature also makes them slower to adapt to network failures. Troubleshooting a network running RIP requires a careful review of both connectivity and protocol-specific behavior. Ping is used to verify basic communication with next-hop devices. Traceroute helps identify whether a packet is being forwarded along the expected path. Viewing the routing table with commands like Show IP route reveals which routes have been learned dynamically and how many hops away they are. You can also check RIP-specific statistics to see when the last update was received and which interfaces are participating. These tools collectively give you a complete view of what RIP is doing and where it might be falling short. Administrative distance determines how routers choose between multiple routing sources when more than one route to the same destination exists. RIP has a default administrative distance of 120, which means it is less preferred than static routes or more trusted protocols like EIGRP, which has a value of 90, or OSPF, which defaults to 110. When a router receives two conflicting routes, it uses the one with the lowest administrative distance. This principle ensures consistent routing behavior and helps prevent instability caused by route ambiguity. It's a key concept in any routing scenario. One of the more frustrating challenges in distance vector environments is route instability. Because RIP routers rely on periodic updates and have no centralized view of the network, they may take longer to recognize a failure or change. During this period, they may continue to forward traffic down invalid paths or fail to use available alternatives. This problem is exacerbated in networks with redundant links or asymmetrical paths. Adjusting timers and implementing triggered updates can help reduce this delay, but it does not eliminate the core issue. Route instability is a known limitation and one of the main reasons RIP is considered obsolete in larger designs. To improve loop prevention, RIP includes a technique known as split horizon with poison reverse. Under the split horizon rule, a router does not advertise a route back out the interface from which it was learned. This helps prevent a route from being relearned in reverse, which could create a loop. Poison reverse enhances this mechanism by explicitly sending back the route with a hop count of 16, marking it as unreachable. This ensures that neighbors know not to use that path again. Together, these techniques minimize the chance of routing loops while speeding up convergence. Despite its limitations, RIP remains an important part of the distance vector family and a valuable concept for certification study. It exemplifies the behavior of simple routing protocols that depend on direct neighbor communication and minimal metrics. RIP's predictable update schedule, its use of hop count, and its methods for loop avoidance all serve as excellent instructional models. By studying RIP, you build an understanding of how routers make decisions, how updates propagate, and how route validity is maintained or lost over time. To summarize, distance vector routing is defined by neighbor-based learning, hop count-based metrics, and periodic full-table updates. The Routing Information Protocol is the best-known example of this routing method. While outdated for most modern enterprise applications, RIP continues to be used in limited environments where simplicity and predictability are more important than speed or scalability. Learning how RIP operates provides insight into how routers communicate, how they adapt to network changes, and how they avoid loops. These principles apply even when you move on to studying more advanced protocols. To conclude this episode, remember that RIP uses distance vector logic, which means it calculates routes based on how many hops are required to reach a destination and which neighbor can take you there. Routers using RIP share their entire routing tables every 30 seconds, which keeps the network informed but also leads to inefficiencies. RIP simplicity makes it great for small networks and education, but its slow convergence and 15-hop limit make it unsuitable for larger, complex environments. Understanding how distance vector routing works and how RIP implements it is fundamental to building your knowledge of dynamic routing and preparing for deeper networking topics. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, Make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.